Today I wanted to talk more about solving DC circuit problems and how, what the first simple approaches we might take to that sort of thing. Before we go into that, I want to talk a little bit about the, visual vocabulary of circuit diagrams, since I haven't covered everything about that. So, in our DC circuits, we have only a few different components, but there are several different symbols that are drawn for some of these components. So the first is a DC voltage source. So most commonly I use the following symbol. So I draw a symbol that looks like that, where one side is longer than the other. So the convention here is that the side with the longer line is positive, the side with the shorter line is negative. The positive and negative are sometimes, but usually not, drawn next to it, so it's understood that that's the positive negative direction. And sometimes when we see this, there's a voltage written next to it, 6 volts. So this side is 6 volts higher than this side. Sometimes it's not written, and sometimes it's what we're trying to find, or whatever. We also see this symbol, which is very similar to the left one, but the long short is repeated. This is meant to represent a battery. Sometimes it is just used for a generic DC voltage source also. The idea of the battery here is that it's showing that you have multiple voltaic cells, the chemical components of a battery, multiple of those in series, creating this potential difference. Otherwise it looks exactly the same as this, long side positive, short side negative. The other one you see, and this is going to show up in our simulation software, I believe, is a symbol that looks like that, just a circle with a plus on one side and a minus on the other. And there it's obvious which side is which. We also might run into current sources, where instead of this, which provides a constant 6 volts to our circuit, we might have something that is providing a constant flow of current into our circuit. Maybe it's pushing 10 milliamps into the circuit, and it doesn't care what the voltage is, or more on that in a second. So the symbol for a DC current source is a circle with an arrow in it, and that arrow is pointing in the direction of the current flow. So you might see something like this connected, to some circuit, and this is telling you that this is making 10 milliamps flow in that direction. Right. So those are our sources of electrical voltage and current, but of course, voltage sources flow current out of them, and current sources create electric potential differences, create voltages. It's just a matter of which one of the two it is telling you, or which one of the two it is imposing on the circuit, and the other value is allowed to be whatever it has to be to get the rest of the circuit to solve. Okay, we also have resistors. I'm not going to talk too much about resistors because we already know them, but this is our symbol for resistor, zigzag line. I guess full disclosure, in European books, they use a rectangle for a resistor. I think that's silly and refuse to do it. We will use rectangles later on in AC circuits, but that's for something slightly different. Okay, lastly, we have ground symbols. So our ground refers to the point of our circuit that we are defining as 0 volts. In real life, this can mean different things. This could mean a physical connection to the earth, what we call earth ground, literally a wire going from your circuit, probably into the wall, to the circuit breaker panel, and then to some ground rod, some piece of metal that is pounded into the actual earth. Or you might just have a kind of arbitrary part of your circuit that, okay, we're saying this is 0 volts and we're measuring everything relative to that, but your circuit doesn't have any wire connected to the earth, right? Maybe a battery-powered circuit in your cell phone or some remote control, right? Whatever you're calling 0 volts there is very arbitrary. It has no physical connection to the things around it. Okay, so our different symbols for ground are the following. This one is the most common, and sometimes this is used generically, sometimes this is used to mean only those grounds that are actually connected to the earth ground. We're not going to worry about that distinction, we're not going to worry about that distinction in 315. Another symbol you see, and that I think might come up in our simulation software, is just a downward pointing, like hollow triangle. So this symbol also means ground, but this means signal ground. So this might just be, something that you are referencing as 0 and, kind of making an arbitrary decision to call this point in the circuit 0 rather than actually connecting it to something special. Okay, and the other ground symbol, which we will probably not see again, looks like that. That is a chassis ground. So if you have a electrical device that is in a metal box, for safety reasons, you want to connect your ground to the metal box of that container, and that connection is shown by that symbol. Chassis ground. All right, cool. So when I taught Physics 211, and often when other instructors do too, we get away with not using these ground symbols, and we draw circuits that look maybe kind of like this. We have a voltage source and a resistor and maybe another resistor, and our voltage source is connected back to our resistor by some wire. And when I teach 211, I explain that this wire on the bottom, we're just going to decide to call it 0 volts, and then this is at some higher potential, this is at some potential between the two because of these two resistors. And this is a perfectly fine way of drawing this circuit. It turns out, especially later in this class, it is going to be much more useful to not draw our circuits that way and instead draw our circuits like this. So instead of drawing this wire that is at a potential of 0 volts, I'm just drawing two ground symbols to show this is at 0 volts, this is at 0 volts, and these ground symbols can have as much current flowing in or out of them as they need to, just like that wire would have. So functionally, this is no different than the other picture. If we were using this to refer to the earth ground, this would mean those are actually like plugged into the earth itself, but again, we're not worrying about that distinction. We're just going to use this as our generic 0 volt ground symbol. Okay, so yeah, both of those circuit pictures are equally good, but this is going to be easier in some circumstances, so I want you guys to get used to seeing and thinking about circuits that look like this. All right. Before we get on to solving circuits, there's another thing I want to talk about, and that is the ideal versus real behavior of circuit components. And we'll have lots more to say about this as we add more tools to our toolbox. But here's where we'll start. So, for example, we have a voltage source symbol that looks like this, and maybe we'll just say this is 12 volts, right? So on paper, if I connect this voltage source to we'll make this easy, to a 12 ohm resistor, I get a current flowing in this circuit that is 1 amp of current, right? Okay, easy enough. That's Ohm's law, V equals IR. Okay, so if I replace this with a resistor that is 0.12 ohms, and you can certainly get, you can obtain resistors this small. This is not a crazy thing, or you can find a piece of wire and measure it and figure out how big it should be to be 0.12 ohms. Again, on paper, the current we would get flowing in this circuit is 100 ohms, or excuse me, 100 amps, which is a lot of current. And that is the correct answer for this circuit, but let me ask the following question. If we had a 12 volt battery, like in real life, and we connected it to these resistors, are these the results that we would get? Well, the answer is it depends on the battery, or it depends on what this actual voltage source is. So something like a small 12 volt, what they used to call lantern batteries that were like, this big. If you connected a big resistor to that and it only had to flow a little bit of current, it would be able to supply that current. But if you tried to put a small resistor on it like this, there is no way you get 100 amps out of that battery. And that is because of some internal constraints that we'll talk about in a second. But if you have a big DC power supply or something like a car battery that is designed for higher amounts of power, higher currents, and you connected a small resistance to it, you might get 100 amps or close to 100 amps flowing in it. Car batteries, I don't know that they can put out 100 amps for long periods of time, but I think for short periods of time they can. Yeah, okay, so the point is, voltage sources in real life aren't necessarily able to supply an infinite amount of current, right? On paper, this symbol means ideal voltage source. It can supply any current necessary to keep this voltage at whatever it's supposed to be, 12 volts in this case. Okay, so how can we represent or account for this difference between what we have on the board and the actual behavior of our batteries or power supplies? So the way we can think about that is with an internal resistance. So instead of our battery just being, instead of our battery just being this piece, now our battery is this whole thing, which includes an ideal voltage source in series with some resistance that we will call RS for series resistance. Sometimes this is also called the internal resistance of a battery or power supply. And the effect of this is that when we connect this to our load over here, if we connect it to some large resistance, we will say our resistor is big, that means we are not going to have very much current flowing. And as a result of that, if there's a small amount of current flowing through RS, we're not going to get a very, very big voltage difference across this RS. Contrast that with if we replace this with something like a wire, we ask for as much possible current as we can get out of this. We're going to have a lot of current flowing through RS, and in fact, we're going to have a voltage drop across RS that is just equal to our battery voltage. So these are kind of two extremes. If we don't want very much current, then we get the full ideal voltage of our battery at the output of the battery. As we ask for more and more current, that voltage decreases and decreases until at this extreme, all of our voltage is dropping across this resistor, and we have no voltage across the terminals of the battery. There will be a lot of current flowing, but all that's doing is dissipating heat in this series resistance, and the effect of that is causing our battery to heat up rather than doing anything useful. So lower series resistances are better. So things like car batteries have much lower series resistances, a fraction of an ohm, than like alkaline batteries, like what ones do I know? C or D cell batteries, I think, have internal resistances of roughly an ohm or maybe half an ohm or something like that. And things like AA's or AAA's, they might have internal resistances of a few ohms or something like that. So if we were to graph, let's imagine now that we have a resistor connected to this that we will just call the load resistance. So this is some resistor that we have connected to our battery. This could be, a resistance representing a motor or a light bulb or whatever. And let's say the voltage between these 2 points we are going to call VL for the voltage reaching this load resistance. And I guess we'll call it V load, why not? And lastly, I'm going to call the voltage of our ideal source here, I'm going to call this V, we'll call this V ideal or something like that. So maybe this would be the labeled voltage on the battery or power supply, so 12 volts for our car battery example. Okay, so if we wanted to make a graph of the voltage that we get across the load as a function of this load resistance, it changes, right? We saw in the example I just did, if our load resistance is 0, so these 2 points are shorted together by a wire, essentially, then, you know, we have our ideal battery voltage, 12 volts, increasing from here to here, and then that same 12 volt decrease from here to here, and 0 volts left between those 2 points. So at 0 resistance, we have 0 load across, 0 voltage across the load. As this resistance increases, our voltage increases, and for very high values of this resistance, it is always going to be just this battery voltage. So if we have very little current flowing, then we have very little drop across this internal resistance, and so most of our voltage drop is happening across this load. So as we increase the load resistance, we asymptotically approach this, this ideal value. Okay, so let's make that look more asymptotic. Okay, so what does that mean? That means that if we are, you know, connecting a battery or power supply to a circuit, we want to make sure we are not asking too much current of that power supply because we may not be, you know, getting the voltage that we're asking for.